So welcome to this talk about threading. So it's an advanced talk. So it's for people that already know a bit about Qt and about programming and a bit about thread as well. It's not going to be an introduction to thread. It's about, but let's start. So before starting, I would like to talk a bit about me. So I'm from Belgium, near Liège. So yes, I speak French, if you ask. While I was a student, I was helping the KDE project. How many of you have heard about this project? Ah, good. So being a KDE developer led me to work for Trolltech, to work on Qt, which later was acquired by Nokia, still working on Qt. I've worked on many things in Qt. I was maintaining the Q style sheet style, the items view. I ported the Qt script to JavaScript core and then to V8. And yeah, I helped to code the QML debugger and many other things within Qt. So I'm kind of like generalist. I don't work in a very specified area. But I recently left Nokia to start a company with a friend. So we offer Qt services, just this slide. So we're not here to talk about me, but we're there to talk about threading. So I look up the definition in the dictionary, but that's not what we're talking about. We're obviously talking about the computer thread. So in this presentation, my goal is to do a bit of reviewing of threading with Qt, and I would like to introduce you to log-free programming. How many of you know how to do log-free programming? Not many, and that's perfect because it's really an introduction, so it's just to discover new horizons. And then if I have time, I would like to talk a bit about QMutex in Qt 5. So let's start with a short introduction. When to use thread. So there is two main reasons, I think. There is probably more. One is when you have expensive CPU operation and you want to use the multiple cores that the CPU have nowadays. And the other is to keep a responsible user interface. And I will show a demo about the responsible user interface later. So are you familiar with those classes? That's basically what Qt provides. Some low-level classes like QThreads, QMutex, and so on, and some more high-level class like Qt concurrent, which I really recommend to use. And then those two classes at the end, QAtomicInt, QAtomicPointer, they are the class that I'm going to talk about when talking about log-free programming. So I would like to do first a little demo. So let's try this. Oh, cool. So I made some, I'm not a designer, so so I was told with QML it's really easy to design. You just do something and then it's beautiful. And I did something and yeah, almost. So there I can compute the Fibonacci number. The third Fibonacci number is 3. The fifth is 8. Sorry for that. Yeah, the 40th Fibonacci number is, wait a moment, that's it. And here we have the problem that when I was pressing OK, it stopped turning. So yeah, the application is there. So I don't need, oops. So basically I have one text so that's the Fibonacci number. It's the fib property of a Fibo object that is in the C++. We're going to see this Fibo object later. So if it's 0, I show loading. If it's not, I show the number. And then I have just a text, and when I press the OK button, I say on the Fib object, I compute the Fibonacci number of the input. And now we see how I compute the Fibonacci number. So are you familiar with this function? I suppose so. And yeah, that's not the best way to compute, but we are not going to optimize it for now. I just needed some slow CPU and TTIF operation. And the interesting thing is this Fibonacci object, which has a fib property with a fib changed. So if you're familiar with QML, this is basically how you integrate C++ code with QML. You just export some object that have some property. So yeah, and yeah, the code do not really, this code is not really important. The thing is, when we call compute fib, we call the Fibonacci number in the same thread, which is going to be too slow and block the UI. So I'm going to change that, and instead of setting the Fibonacci number, instead of calling the function directly, I'm going to set it to 0, so then that means it's going to be loaded. And I'm going to use QConcurrent run to run the Fibonacci function. So basically this means I'm going to run the Fibonacci function with the parameter f in a different thread. And I'm also interested in the result. And what is the result of QConcurrent run? It is, well, it's too small, but it's basically QFuture of int. So I will store the result of this call to run is a QFuture, which means that the result is not computed yet, but it's going to be computed in the future. And then I would like to be notified when the result is done, so I'll add a slot. I call it callback. And then oops. I should be consistent in naming. Dot result. So this callback is going to be called when the future will be ready. And when is going to, how can we know when the future is ready? We're going to use QFuture watcher. And in the constructor, we're going to connect this mwatcher signal. Slot, of course. So we're going to connect this watcher when it's finished to the callback. And the last thing we have to do is to say that we're going to listen this future. OK, so I think we can try that. Let's run the application. And now, well, if we compute some small number, it still works. And 40, it says loading. And you see the UI is still responsive. And we have the big number. Is there any question about this? Everything is known maybe from before, or it's too difficult. But so yeah, that was the demo. And now the second part of this talk, log-free programming. What is it? Log-free programming is basically to try to do your algorithm without any lock. So what are the locks? That's basically the mutexes. And what's wrong with the mutexes? Well, they're fine. Most of the time, it's just the right thing to use. So don't take my talk as I should never use mutex. That's not true. They're perfectly fine. But there are some problems. One of the main problems is that if you have a computation that is computed or if you have a parallelized computation, then one thread will acquire the mutex, and then maybe will be descheduled by the CPU, no, by the OS, which means if there is some page fault or if the thread arrives at the end of its time slot, then it's going to be put in pause, and then while having the mutex acquired. And that's really bad because all the other threads that want to also acquire this mutex will have to also be descheduled and wait for this thread to be scheduled back. So we have more context switch that wastes CPU time. And then another good reason to use log-free programming is if you do real-time application. How many of you do real-time application? Quite a few still. I was expecting less for GUI programmer. But so in real-time application, you have all kind of problems like priority inversion, unsafe interrupt handler, because you cannot use a lock that could be locked by a thread in an interrupt handler, or convoying, which is a bit what I explained, that all the even high priority tasks are going to be slowed down by the slow priority, the slow thread that acquire the mutex. So then there is the log-free programming, which doesn't use locking. So they're usually faster, and you don't risk a deadlock. And so even if the thread is killed if there is no lock, the thread cannot be killed while holding a lock, which will be causing a deadlock. And there is not only good side, it's also log-free programming is a bit more difficult. But I think it's also more fun, which is why I want you to discover this way of programming. So the way it works, we're going to use QAtomic int, QAtomic pointer, and each thread is going to advance, helping the other thread without needing to lock. So I'm going to give a small introduction on the QAtomic API. Then I go and explain an example. I will develop a log-free stack. And I explain the ABA problem later. You will see what it is. So this is the API. It's basic. So we have two classes, QBasicInt and QAtomic pointer. And those classes are very similar. They all have a set of functions, which is composed by a function like test and set, and associated with a memory ordering. So you mix and match, and you get, so for example, test and set acquired, fetch and ordered. So you have all those combinations. So let's go deep into each of those calls. Fetch and store, it's basically going to swap the value and return the previous one. So I used some code here, but this, of course, is not atomic. The real implementation is implemented in assembly. So it's perfectly atomic. And it's atomic, which means that the state will be coherent on each of the threads. So for example, if two threads are going to do fetch and store in the same time, only one thread will return the old value, and the other one will return the value that has previously been set. So we have fetch and store. We have fetch and add, which is just like plus equal, but in an atomic way. And we have test and set, also commonly known as compare and swap, if you read the literature. So test and set will change a value from one value to the other. So we need to pass the expected value, and it's going to check if the value is still the expected value, and if it is, replace it by the other. Meaning that if another thread in the meantime change the value, then the operation will fail and return false. So it's only going to return true if the operation had succeeded and the old value is replaced by the new value. And then we have the memory ordering. So what is it? You probably know that this modern CPU have what's called the out-of-order execution, which means that what happens in the CPU is not really what in the order of how you programmed it. So the CPU will basically fetch at each cycle, fetch some instruction to some instruction cache, and then the wire inside the CPU will try to compute the dependencies between all those operations in order to schedule all those operations to different computation units. But the way it's scheduled to the computation unit is not in the same order as how you programmed it, which means you could, if you write x equal 1 and y equal 1 in your program, you never know which one will be written first in the memory or how the other threads are going to see it, which is why you need to specify the memory ordering. So there is 4 modes of ordering. Ordered means that no operation are going to be moved before or after the atomic operation. Relaxed means that this API do not offer any guarantee, so everything can be reordered. And then you have acquired, which means that everything that is after the atomic operation will happen after, and release, which means that everything that is before will happen before. Is there any question? So let's get our hands dirty and develop a stack. So I made some nice graphism here. So this is a stack, right? So we have a pointer to head to the first node, and each node has a pointer to the next node. And if we want to push a node to the stack, so in this case we want to push the node C, we just say that the next one is the current head, and then we're going to change head from B to C. That's something you probably, if you're a computer scientist, you must know that, I think. But what happens if we have 2 threads that are each going to push one node? So thread 1 wants to push the node C, so it says C.next equal B. And same for thread 2. They both do the same. But they're going to do each of them are going to do an atomic operation to change head from B to C. And in that case, thread 2 goes first and manages to push its node C, which means that the atomic operation in the thread 1 will fail because head is not B anymore as thread 1 will expect. So the operation fails. The thread 1 is notified of the failure and is going to retry to push the node C, but this time using D as the next node. Yep. And then the pop is as easy. So the thread is going to try to replace head from B to A. So, oops, that's a spoiler. That's the need. So I made a small program here that uses a stack. So this program will, at first point, push a lot of nodes into the stack, and then at a later point, pop all the nodes and destroy them. So here I've inherited from Qthread because I want to have really control over what I'm doing here, and it's really a simple function. So run each. So I'm going to start here 2 pusher threads, which each are going to push a huge number of nodes. So allocating your node and pushing it to the stack. Then the popper thread do the other way around. Until there is no more node to the stack, we're going to pop them all and delete. And then, so I start an elapsed timer just to compute the time. So I start all the threads, I wait for them to finish, I compute the time, then I start all the threads that are going to pop and do the same. So let's see how that runs. So I'll just make. So it took 700 milliseconds to push all the nodes and 2.5 seconds to pop them. But so here I have 2 threads because it's a dual core. And the stack currently is implemented with a mutex. So this is how you would implement a stack with a mutex. And what I'm going to do now is to change this stack, and I'm not going to use a mutex anymore. It's lock-free, so no mutex. And instead of using a direct pointer to the node, QAtomic pointer to the node. So QAtomic pointer is just like a pointer, but with atomic. So in order to push, so we're not using a mutex. We're going to push in a loop. So what does that mean? That means that I will try again until it succeeds. So I expect, test and set ordered, I put the expected value and then the new value. The expected value here is the value that we stored in n.next, and we want to replace it by n. OK. Is there any question on the way we implemented push? Because we're going to implement pop the same way. So no mutex locker. Yes. So same thing. I will do the operation if it works. So we want to have the head. We want to have the node that we return. So that's n. That's the expected value, and the new value is n.next. Mistake. It's missing a parenthesis. OK, so let's see how fast it is. So this is with two threads because I have 2 core. And as we see, so instead of 600 milliseconds to push, we're in 400 milliseconds. And the popping was even much faster, from 2.5 seconds to half a second. and that's only with 2 cores. And we can expect the more we have cores, the more we have threads fighting with each other and trying to acquire the lock. So the more we have threads, the more we can expect the gain in contention to be big. And well, this benchmark is a bit, because I'm benchmarking 2 things here. I'm benchmarking my stack, and I'm benchmarking also the new and the delete, which I also do. So I basically do a lot of new and delete. Is there any question on this? Really, no question? Everything is clear? So if there is no question, I'm going to ask them, because yeah, I had some interesting question at the rehearsals, which I think is good. One of the questions was, why did I use test and set ordered and not, or how do I know I use ordered, or should I use acquire, should I use relaxed? And here I used ordered because, as I said, if you're not sure what to do, use ordered, because this is the more strict. So it's you should be correct if you use order. Not necessarily the fastest, and it depends really on what you want to do. So in this case, we want to push nodes, so we expect that the node that we push are done. So I mean that everything that was like, I suppose in a real case, you want to put some payload in the node. So you want the payload to be completed. So in the push, you will maybe use release to say, OK, no, all the operation that was computing the node are now done before we push it. And for the pop, that's the other way. Before using the node, you want to be sure you really have popped it. So you would probably want to use acquire there, but it's really not that important, because I would suggest to use ordered, and then you're safe. No other questions? So I will do it. So the question is it faster if I compile and run? And it's not going to be faster, because I'm here using, or I don't expect it to be faster, because it's using an Intel Atom CPU, which for which there is no really need to have memory barrier anyways, because they have a more strict ordering. But if you try on ARM, it might be faster. OK, so if there is no question, so this is basically the way. Oh, many questions here. So.
Please talk into the microphone. Is it OK?
I have a question about the priority of these threads. So is it in sync that if you push with these 2 threads, that they are pushing the same amount of?
Yes. So in that case, they're going to push the same amount, because by construction, they all push the same amount. And indeed, one thread might pop more than the other, so the way the popper works, it also counts the number of threads, the number of nodes each thread is popping, and there in the code that runs the thread, so I run all the threads, I wait for them, and I compute the total of nodes that have been pushed, and I also do like the difference between the average. And we can see that's this number here. So so there's 6 million nodes that have been popped, and so the average is 3 million. So in average, each thread, so one thread here has pushed 3 million plus has popped 3 million plus that number of nodes, and the other one has popped 3 million minus that number of nodes. So it's kind of okay. I mean, it's roughly they're roughly all working the same here, all popping the same number of nodes. Does that answer your question? Yeah. Good. No other questions? Well, let's continue then. The ABA problem. So my code is nice, but it's unfortunately not correct. So it works here because I push all the node and then pop all the node, but in real time, in a real stack, you might want to support that threads both push and pops nodes. So let's see what happens here. We have the thread 1 is going to pop a node. So because A is the first, head points to first, so head point to A. So the thread 1 is going to save that he needs to return A, and will try to atomically change head from A to B. But then just before the atomic operation, that thread goes to sleep, and the threads 2 do a bit of work. So the thread 2 just popped A. So what would happen here if the thread 1 would wake up? What would the problem be? Well, there would not be any problem because head, the atomic operation would fail because head is not A. So in that case, the thread 1 would retry and would probably pop B. But the thread 1 do not wake up at this point. The thread 2 continues to do some work and push a new node C. Again here, if thread 1 wakes up, no problem. Head is not A, so the atomic operation will fail. But thread 2 continue to do some work and pushes the node A back to the stack. And then what happens if thread 1 wakes up? The atomic operation succeeds. So A is popped because head was equal to A. And so we have this. What is the problem here? Well, the problem is that thread 2 thinks the node C is pushed, but it's actually not really on the stack, so the node C is leaking. It would have been even worse if the thread 2 would have popped B, and then B will the stack would still contains B that is not supposed to be in the stack anymore. So yeah, so is that clear? Yep. So of course there is a solution to these problems. So what are those solutions? So one of the solutions is to add a serial number with the pointer. So we can try to align the pointers so we have some bits free at the end. We need at least 3 bits, and I would say even more. But so if we can align those if we can align those pointers so we have some 0 at the end, we can add a serial number that is incremented each time we push. So then it's not the same anymore because the serial number will change. If there is no way to align, instead of using pointer, we can use index to arrays. So we can have some bits for the index to the array and some other bit for the serial number. Some architecture supports multiple word compare and swap, or you can even do a multiple word compare and swap using a normal compare and swap. There is some paper about it, and you can search for it on the internet. Hazard pointer is also a great algorithm in which each thread has a public list of pointer he wants to access, which means that the other threads can check that the other threads don't want to access this pointer. So it's a bit out of the scope of this presentation to show you how that works, but you can read on the internet about it if you're interested. And then some architecture have this, so PowerPC, for example, load linked store conditional, which instead of being a compare and swap, when you load, you flag the memory saying if it changes, then the conditional store will fail. But this is not really available on many CPUs, and you're also limited of the operation you can do between the load and the store. So yeah, solution exists. You just need to be aware of the problem and while implementing your data structure to solve this problem. Is there any questions? So now I'm going to talk about QMutex, how it works in Qt 5. So in Qt 5, QMutex, we wanted it to be a POD. So without a constructor, which means that it can be used in a global data. Because there's a problem if you use objects with a constructor in your library as global member, just on top of the class, or a static object, static member of class. The problem is that that's not really the topic of this talk, but the problem is that you don't really know in which order all the objects are going to be initialized, especially on a library. And also you pay some cost of this initialization. If you use the library, even if you're not using this part of the library, you're going to pay the cost. So it's much better to have them in a POD, so it's initialized at compile time and there is no runtime cost. And if you know a bit of the Qt internals, you know that each object is basically just a pointer to the implementation, which is in the private data. And so QMutex in Qt 4, when you create a QMutex, it has to allocate this QMutexPrivate. It has to allocate some resources to handle the mutex for the platform-specific code, and we don't want that. So in Qt 5, QMutex, the only member, so the only member is an atomic pointer to a MutexPrivate so in Qt 4, it's a pointer to a MutexPrivate, which is always a MutexPrivate, but in Qt 5, this pointer is not always to a MutexPrivate. Indeed, there is two special values there. So by default, it's initialized to 0, which means the mutex is unlocked. So if the address of D is 0, the mutex is unlocked. And if the address of D is 1, this is a special value there, then the mutex is locked, and we're guaranteed that there is only one thread that has the lock, and no other threads are waiting for this mutex. And then if it's a pointer to some address, then it's a pointer to QMutexPrivate. So this pattern allows you to do the try lock. So the try lock is basically trying to change D from 0, so from the unlocked state to the locked state. If that worked, that's it. We have the lock. If it did not, then we have to do a bit more. I'm going to explain later. And the unlock is the other way around. So the unlock switch back to 0, and if it was 1, so fetch and store release here will set D to 0, and if it was 1, then we're done. No thread was waiting, so we don't even need to go to the system or to do anything. We just return there was no contention. But if copy was not 1, it means it was a pointer. It cannot be 0 here because we were locked. We cannot unlock a mutex that is not locked. So if it's a real pointer to a MutexPrivate, then we need to wake so we need to wake, which means all the thread that were waiting will try again to change D from 0 to 1. And then we deref because we're going to try to release the MutexPrivate. So yeah, here I'm presenting a simplified algorithm. This is not really how it is in Qt 5 because on Qt 5 we tried to solve even more problems that I don't want to get into in this presentation. So you saw the deref at the end. So indeed, the mutex private is ref counted. We cannot delete a mutex private. The reason is when we're going to lock, we're going to read the address of the mutex. We'll see, OK, that's an address. And then we can go to sleep, and we can unlock the mutex, which means that the mutex private might be used for something else. And we don't want it to be released, because if we call delete on it, then when the thread will wake up and try to access this mutex private, we will access some release memory. That's not good. So we can never release a mutex private. So instead, we push them. We're going to push them in a stack, a log-free stack, as the one we saw. It's a bit different in practice, but the concept is the same. And we don't expect to have many mutex private in this free list, because at any given point we can have not so many mutex holds. Like you can only have contention in the number of threads you have. So you should not have in a given point more mutex private than you have threads. So the ref count here is a bit special, because we don't want to ref if we were already equal to 0. So the ref count is basically we basically want to increment atomically, but not if it was equal to 0, and we return false if it was equal to 0. And the deref will deref the ref count and release if the ref count reaches 0. So release is just push the mutex to the log-free stack, and when we will allocate it a new one when we lock, we will return a new. We will try to pop from this log-free stack, or we will return a new one if the log-free stack was empty. And then we have some platform-dependent code here, so wait and wake, which will basically either wait on this mutex until the other thread wakes up. And an important point here is that if you wake up and then you wait, then the wait will do nothing. So once you call wake on a mutex private, an equal to wait will just return. And then the complicated bit, and yeah, it's the lock. So the lock is in a loop, and we'll try to change D from 0 to 1. So that's the try lock. If it succeeds, then we're done. If it does not succeed, it means we need to wait. So we're going to try to replace. So there's several cases here again. So we make a copy on the stack. This is important because we don't want the copy to change behind our back. If copy was 0, it means that in the meantime, the mutex has been unlocked, so we can try again, continue. If the copy was 1, it means we need to allocate a new mutex private and try to switch it with D, so copy here must be 1. So we try to change from 1 to this new mutex private. If this does not succeed, it means either we've been unlocked already, or another thread is also waiting. So we're just going to continue. So we're releasing the new, and then we continue. And then we will use this new as the copy. So if this succeeds, so if copy is really a mutex private, we're going to try to reference it. If the reference count was 0, so if this returns false, it means another thread has the other thread has unlocked the mutex. So the mutex private is not used at the moment. So we can continue. We retry. if the reference count was 0. And then after we have refed, we need to check if we refed the right MutexPrivate, because again, the MutexPrivate the mutex might have been unlocked and then reused in another mutex, and we want to wait on the right mutex. So if D here, that's the atomic pointer, is different than copy, that it means that the mutex has been reused. So again, we're having the wrong one, so we need to deref, and we start over. And then only we know that we have the right MutexPrivate, that we have a reference to it, meaning it's not going to be reused. So we can wait on it. And if it already has been waken up, then wait will just return, else it will wait. And once we've finished waiting, we deref, and we start over. We start again to change from 0 to 1. That's complicated. That's a lot of code. So I would be surprised if there is no question. Question?
Is this fast?
So the question was, is this fast? And so this is not slow in the sense that compared to the wait, so we're going to block and do a context switch and all that stuff, that is going to be slow. The thing that is going to be fast is this part is going to be fast, because it means if you're developing a library and then you have your class and you don't know if the user is going to use threads or not, you anyway need to use a mutex even if there is no thread involved. And then we see that if there is only one thread, the try lock will always succeed. So it's going from 0 to 1, and that's fast enough. And the unlock will also be very fast, so changing from 1 to 0. So in the case there is no contention, it will be no call to the system, and this can even be inlined. So there is not much overhead of using mutexes. But the main advantage is that QMutex is just a pointer, so you can have many of them. They don't use many resources. So more question? But this is not exactly how Qt5 is, because there is some problem. Like in practice, we don't really want to wake all the mutex, all the threads that are waiting. If you have 5 threads waiting on the mutex, when you unlock, you don't want to do 5 context switch, while obviously only one is going to get the mutex again. Another thing is QMutex has an API to try lock with a timeout, and this approach wouldn't work with a timeout. And it's also not fair, meaning that the first come, first serve thing, it's not fair because one thread might want to acquire the mutex, and then another thread want to acquire the mutex. They both block, and then on the wake up, maybe the second thread goes first, and that's fairness. And as I explained here, it's not fair. So we've solved all those problems in Qt5. So it's really similar to that. You can saw the code and you will recognize most of the things, but there is some tricks to support try lock, to support recursive mutex as well. And on Linux, we use something called Vutex. So we don't even need QMutexPrivate, because Linux has this really nice concept of Vutex, which is some system call that does what I described here basically for us. So is there any question? Because that's it for me. So questions? Yes, there's a question here.
The question is, what would you suggest or recommend as a portable solution? I mean, you mentioned Mutexes, which are available on Linux, but as far as I know, not on Windows or other platforms.
Well, it uses QMutex then. So in Qt 5, QMutex...
Simply fall back to normal QMutexes.
Yes, because
okay.
QMutexes will use Mutexes on Linux.
Ah.
And yeah, and
okay.
So that's the backend. Everything that I explained there about Mutex in Qt 5 is on every platform but Linux, because on Linux we use Mutexes directly. Okay. We already use Mutexes in 4.8, so, but not as good at, because we still need a QMutexPrivate in 4.8, but not in Qt 5.
Thanks.
Okay, so thanks for listening, and if you have any question, just I'll be in the support desk later, and please provide feedback as well. There is a feedback stand you can go, and I'm interested by your feedback. So thank you.